encourage you, or those of you who are interested in checking out the repo to see what you can do with this. And these kind of players, you'll see them emerge. I mean, to a certain extent, you can already see them. They're not fully proven, for example, but there's a bunch of games who are running their own chain. One of them is Roll Your Own by Cartridge, which I encourage you to take a look at. It's a fun game that runs its own chain. Now, the second kind of layer 3 that you're going to hear about, that you may have heard about, is Kakarot. So Kakarot is another chain. It's, well, to be more specific, Kakarot is a set of Cairo smart contracts that are able to emulate the behavior of an EVM chain and interpret EVM bytecode. So these smart contracts, they could be run on the public Starknet, and they can also be run on a sidechain. And Kakarot most likely will operate as an L3 on top of Starknet. So it's a sort of ZK EVM built in Cairo. It's not a type 1 ZK EVM, meaning that it's not doing exactly, it's not proving the exact EVM, but it's emulating the EVM in Cairo. Now, yeah, that's what I meant to say. So the space between L2 and L3 is not discrete. And I'll expand a little bit on that. But what you're doing with an L3 is essentially running a chain and proving that you run that chain correctly. But maybe running a chain is not what you need for an application. And actually, the simplest example I have of this is, for example, StarkX, which some of you may have heard of. StarkX is not a blockchain. It's a state machine that transitions from state to state and is operated off-chain. If you're able to build this kind of machine and operate them off-chain and prove them off-chain, you may run your own L3, which is not exactly an L3. Maybe it's a L2.5. I don't know how to call these, but they're different creatures. They're not proper blockchains. And another really interesting stuff with L3s is that you'll have a lot of really cool privacy things you'll be able to do with them. You'll be able to prove, for example, the correctness of state transition without disclosing the state. So you'll be able to operate private L3s on top of L2s like Starknet. Now, the real cool thing with this is that it's not like other proving system where you have to have your verifier and your code on chain, which is in the language. For example, for Circom. For Circom, you have to have Solidity code and Circom code. With Cairo and Starknet using L3s, you can actually have all your code off-chain executed in the same language that you're using on-chain to verify and exploit those results. So you'll be able to have a much more unified experience in terms of of programming language. All right. So summing up, we have three main entities: sequencers who run the network and aggregate transactions; Hoover, who then make it safe. I'm not sure that's a perfect analogy, but it's hard to say how to find another description of it. But really, like, they prove that state transitions are correct, and they give shortcuts for people to synchronize faster and communicate faster. And nodes use the network. They keep track of the state and they act on it. And they serve the state of the network. For example, if they're an app, they serve the state of the network to their customers. Another important thing that we just discussed is that decentralization right now is still a work in progress. We're not there yet. I invite you to check at the community forum. I think Manmeet will share a link on a decentralization proposal if you're interested in looking at that. And the other thing I want you to remember out of that is that L3s are a really interesting design space. And it's not just about running a chain on top of a chain. There's a lot more you can do with them. All right. Now, I want to talk about transaction versions, and transaction lifecycle. Yeah, feel free to write your questions little by little, but I'm going to pause here a couple of seconds to catch my breath and answer any question if I see them. Arise. But the issue is I'm afraid of being silent, so it's hard to catch my breath, and I just keep on talking. But anyway, all right. So I'm just gonna keep going with the transaction with the presentation. I'm gonna talk about transaction versions. So this part I added recently in the transaction. I hope it's relevant. I think it's important because, you know, a lot of the things you'll discuss in Basecamp, you can learn them from other places. And this, for example, all of this is in the docs. But I figured it was interesting to talk a little bit about it because studying transactions versions gives you insight as to how the network was built and what you can and cannot do with it. So what kind of transactions do we have on Starknet? There are 4 kind of transactions existing in the network and 3 that are active. I asked Midjourney to do a wizard with 3 choices, but somehow he just had 2 torches, but it looks good, so I included it. So right now you have 3 types of transactions: invoke transaction, declare transactions, and deploy account transaction. There is a 4th kind of transaction, which if you build an indexer, you will encounter at some point, which are deploy transaction. I'm not going to get into deploy transactions unless people have specific questions about them. Suffice to say that they're a deprecated artifact of early network days. Now let's look at, and for all of those transactions, there are different versions of them. Let's talk about declare transactions. So declare transactions are the transactions you're using to declare a new class on Starknet, meaning they're really used for you to say, hey, here's a new smart contract that may or may not be deployed on the smart contract. So here that's a wizard teaching a robot a new trick, because you're teaching the network how to do new things. You're just telling it, hey, this is how you can run that smart contract. There are 4 versions of declare transactions. V0 and V1 were the kind of transactions that were used for Cairo 0 contract. So when you were sending Cairo 0 contract, which you were sending is really, you were sending compiled Cairo 0, meaning you were sending Cairo assembly contracts. You were sending Cairo assembly code to the sequencer. The difference between V0 and V1 is that V0 was used before nonces appeared on the network, and V1 appeared after nonces were introduced on the network. For V2 transactions were introduced after Cairo was introduced to the network. So Cairo or Cairo 1, depending on how you say it. So there were Cairo 0 contract, and now there's also Cairo contracts. V2 transactions are a bit different they're a bit different because you're not sending Cairo assembly code, you're sending Sierra code. And the reason for that is if you want the network to use Cairo code, you need to make sure that this Cairo code actually compiles to Sierra, because what you really want with Cairo code is for your code to be yeah, I don't know how much you looked at the difference between Cairo 0 and Cairo so far, so I'm going to try and make it quick. Cairo 0 compiles to CASM, Cairo assembly. Cairo compiles to Sierra, which compiles to CASM. The big property of Sierra is that executions in Sierra can never fail, and they always are provable, whereas execution in Cairo 0 can fail, and they're not provable in that case. With Cairo, with the latest version of Cairo, what we're looking for is a network where every program is provable, whether it fails or not. Meaning you want everything to be Cairo, meaning you need to make sure that everything compiles, everything is Sierra. So when you're declaring Cairo contracts, you're declaring Sierra code, which then gets compiled by the sequencer to make sure that indeed it is a Sierra program and not just a raw Cairo assembly. Okay, so that's why if you look at the, not going to get too deep there, but if you look at what is included in a V2 transaction, there's a bunch of parameters that help ensure that the hash, the class hash you're using, is matching the Sierra code you're sending, because the class hash designates the hash of, it includes the hash of the Cairo assembly code, but you're sending a Sierra code. So you need to make sure that what you're sending corresponds to the class hash you're declaring. I hope that makes sense. Feel free to ask a question there. Yes, if you've used Cairo or Cairo 1 code, you're using V2 transactions always. So, and yes, introducing Cairo instead of Cairo 0 is the main reason why we needed V2 transactions for declare. Now, the second type of transactions in Starknet are invoke transactions. Invoke transactions are transactions that instead of teaching the network how to do a new trick, they're telling the network to do something. So in our case, they're basically like, I wanted to have a wizard invoke a robot or something. So that's the image. And so they're basically a way for you to say, I want this smart contract to execute that thing. Okay. They are used for smart contract execution. They are also used for smart contract deployment. Deployment of smart contracts on Starknet is not done through a specific kind of transactions like on Ethereum. It is done through the use of a specific syscall inside a smart contract. So think of it this way: if you're familiar with Ethereum, if you want to declare if you want to create a new smart contract on Ethereum, you have two options. Either you send a transaction with a specific field in the transaction format, or you call a smart contract that has a factory that deploys another smart contract. On Starknet, there's only the second option. So if you want to deploy a new smart contract, you have to call a smart contract that deploys these new smart contracts for you. Now, luckily, there is public good infrastructure in the form of the UDC, the Universal Deployer Contract. That is basically a public good utility that you can call to deploy your own contract. Invoke transactions come in two forms. One is V0 transactions and one is V1 transaction. So V0 transaction, I was wondering whether I should talk about them or not, given that there's a plan to deprecate them. Actually, they were deprecated a few weeks ago, and then they were reactivated. I'll get into them in a second. So as the network evolved, initially the specs for account abstraction on Starknet were not entirely solidified. So when you actually I'm not going to pull the doc, but if you take a look at the doc, when you send a V0 transaction, you're specifying which smart contract you want to call and which function you want to call, right? You specify the entry point. That lets you call your account contract to then execute something else, or it also used to let you do other stuff before, right? But some smart contracts, some account contracts were deployed with the assumption that you had to specify an entry point and that this entry point could be whatever you like. Now, after that, some additional specs were added on account abstraction, and the current flow for account abstraction, which I think you talked about, was put in place. And the current flow is that your transaction has first to go through validate, then execute. So in your transaction, you need to specify who's the recipient of the transaction, and it's your account. And it always goes through validate, then execute. And then the actual entry point you want to call is inside the payload. That wasn't the case before. That was part of V0 transaction. Now the issue is that account contracts that were deployed when V0 transactions were around, some of them don't have a validate and don't have an execute function. So once V0 transaction gets deprecated, those accounts will be bricked, and it won't be possible to send transactions through them. And V0 transactions have been around, like we wanted to deprecate them for like a year or something, and we communicated a lot saying, update your wallet. But there was an upgrade at the end of summer, and a bunch of people were caught by surprise, and they thought their funds were stolen, something like this, which wasn't the case. Their account was just not following the latest update. But given the backlash, and given that clearly we hadn't communicated properly, the network decided to revert this deprecation, and so V0 transactions are still around. They're a big problem. They're a vector for DOS attacks, so we'll have to get rid of them eventually. There are a few plans, and we'll talk about them maybe in a future session if you're interested. So yeah, that's the main difference between V0 and V1 transactions. I hope that makes sense. Thumbs up? No thumbs up? Questions? Write them in the chat. All right, so we talked about declare transactions. We talked about invoke transactions. Now, what about deploy account transactions? So deploy accounts transactions are kind of weird. They're this weird creature where what happens, your account is a smart contract wallet. So how do you deploy a smart contract wallet if you don't have a smart contract wallet in the first place? You remember when you send a transaction, an invoke transaction, it first goes through validate, then execute. What happens if you want to call a smart contract that is not deployed yet? Invoke transactions will fail. So for this kind of purposes, there's a specific kind of transactions which are deploy account transactions. And these basically have a slightly different flow. I'm not going to get too deep into it, but they have a slightly different flow than regular transaction, and their whole purpose is to let you bootstrap your own account. Instead of calling validate and making sure that they can get paid on validate, they will check that the address you want to execute has funds, whether it has a code deployed or not. And then if that account has funds, it will execute the constructor in a very constrained environment to try and deploy your account, and then call a specific method on it to make sure that it is indeed allowed to deploy that account. And after that, your account will be deployed, and you'll be able to use the funds, right? So it's a very roundabout way of deploying new transactions. Deploying new accounts. Does that make sense? All right, I'm not going to get too deep into deploy accounts. I think it's really important to understand about the difference between invoke and declare, and know that deploy accounts transaction exists, but that's about it. All right, now let's talk about the transaction lifecycle, why it happens once you send a transaction on Starknet. The first step is your transaction is getting prepared, like you prepare it client side. So locally in your browser or in the server of the dApp you're using, you name it, the transaction is prepared. So your software will query the nonce of your account, make sure that it can be included in your transaction. Then your transaction is signed, adding whichever signature you want, and then the transaction is sent. In its current state, this transaction is sent to a node, which then passes it to the central sequencer. Eventually, when sequencers decentralize, there's probably going to be a propagation network, a P2P network that will be in charge of transmitting all of these transactions. The second step is the transaction is queued at the sequencer, right? So it arrives at the centralized sequencer currently, and then it waits for execution. So at this point, before that, if you query the sequencer, it would tell you, no, I have not received your transaction. And at this point, the sequencer will say, yes, I have your transaction. I'm going to get to executing it in a second. So your transaction moves from not received to received. It's similar to being in the mempool in in Ethereum. Now, the difference is that the mempool in Ethereum it changes. So, I mean, your transaction can be top of the mempool, bottom of the mempool, but until it is in a block, you have very little guarantee as to when your transaction will be included. It won't always be like this, but right now on Starknet, the mempool is sequential, meaning that first transaction to arrive is the first transaction to get included. Having higher fees won't get you in front of the line. Okay. Another thing to note, like in the mempool on Ethereum, your transaction has not been taken into account. So if there's a, for example, you're sending transaction with nonce 9, it is marked as received. If you query a node, it will tell you next nonce is 9. It won't take into account the transaction that is in the mempool, kind of like what it is on Ethereum. So Doug is asking, can you explain non-subtraction while we're at it? Does Starknet has future plans to implement it? I hope so. No, non-subtraction is definitely on the list. Okay, so what is non-subtraction? I don't know if some of you have managed with sending Ethereum transactions at scale, but the nonce management is painful on Ethereum. There's a lot of ins and out to it, and I'm not going to get too much into it there. But what you should know is that when you want to send a large number of transactions, keeping on your side track of what is the latest nonce that was added to the chain and what nonces are queued but not in the chain yet, and adapting when one of those transactions randomly gets dropped and having to adapt all of this is a real pain in the back. So one way to deal with that is to have, and that can be an issue either at the smart contract level or at the network level. For a while, nonces were not part of the protocol, but this meant that you could send. There was a way for you to send various times the same transaction with the same nonce, and they would have the same hash, and that's an issue. Nonces on Ethereum are used to sequence transactions, but also to give them a unique hash. So Starknet still uses nonces to give a unique hash to each transaction. But another interesting, elegant way of doing it would be to have something called nonce abstraction. So right now, Starknet, the only thing it enforces on nonces is that nonces have to be sequential. If you're sending a transaction through your account, it has to be the exact number after the last one you send. Nonce abstraction would be a way for you to have this logic at your smart contract level. And one thing I really like, one example of nonce abstraction I really like is having multi-dimensional nonces. Instead of having one nonce, you could have two. And with this, you'll solve already a lot of problems, because if you need to send parallel transaction with the same account, you can just use one as an index and one nonce as the index, and the second one as a way to sequence transactions on those index. So right now, there are plans to solve nonce abstraction on the network, but it's not super high on the priorities list. I hope this answers the question. All right. Now, your transaction was at the sequencer, it was queued, it was received. Now, what happens? So your transaction gets processed by the sequencer. So at this point, the sequencer is just chugging through all the transaction. It picks yours and it says, okay, let me execute that transaction on the state of Starknet. And at this point, if your transaction is correct, your transaction moves from received to accepted on L2, meaning that your transaction will be part of the block. Your transaction doesn't yet have a block number. It doesn't yet have a block hash, but it will be part of the next block. So it is considered accepted on L2. At this point, if you query the sequencer or if you query your node, the state will reflect the fact that your transaction has been executed. So, for example, your nonce will be incremented or your balance will be updated. Now, the second step of accepted on L2 is having this transaction be part of a block. So at this point, nothing changes much for the state of your contract, aside from future transactions that arrive there. But your transactions are attributed a block number, a block hash, and at this point, they are part of a block and they're protected by L2 consensus. And they're easier to query in index at this point. Okay, so it's important to note accepted on L2 right now means there's essentially two sides of it. One before it has a block number and one after it has a block number. Now, the third step on the life cycle of your transaction is to be accepted on L1. Once the sequencer has aggregated a bunch of transactions and he's made a block with it, after a while, there's a bunch of blocks, and those blocks get proven. They get proven individually, and then all those proofs are verified, and the verification is proven, and a proof is generated for that verification. And this proof gets sent to Ethereum. So let's make it simpler. Each block is proven and verified on Ethereum. Verified on Ethereum means that the proof is sent to a smart contract on Ethereum, and if the proof is valid, the smart contract says, yes, it's valid. And that means that at this point, your transaction, which was part of this block that has been proven, is part of the state of Ethereum, and it is now protected by L1 consensus. So your transaction moves from accepted on L2 to accepted on L1. It's important to note that your transaction does not get individually accepted on L1. It's not like L1 validates your transaction, but L1 validates something that attests to the validity of your transaction. And I hope that makes sense. Let's talk a little bit about rejected transaction. So we talked a little bit about this first, right? So in the current account abstraction implementation, transactions go through two phases: validate and execute. And when you think about it, it's the same on Ethereum. Your transaction on Ethereum, first there's a verification of the signature that is opposed to it, and then there's an execution. Transactions on Starknet do the same. They go through validate and then execute. The validate phase, if your transaction doesn't pass the validate phase, the sequencer is not able to charge fees. In that case, your transactions are marked as rejected. They're not part of blocks. For a long time, all transactions on Starknet, regardless of whether they failed in validate or execute, were marked as rejected. Right now, it's only transactions that fail in validate. The transactions that fail in execute are marked as reverted. So currently, in that case, the execution of validate, which transfers the fee of the sequence to the sequencer, is included in the block, but the actual execution is not included in the block. Another important thing to note is that the fact that they failed is not proven, meaning that if validate passes, the sequencer can say whatever it wants. If he says, okay, the execute passed, he has to prove what execute does. If he says execute failed, it doesn't have to prove that execution failed. He can just take whatever fee he wants, up until the maximum fee that was agreed upon by the person sending the transaction. That is obviously not ideal, and it's just a temporary thing, right? And the reason for that is actually really intricate. But you know the difference between Cairo 0 and Cairo 1 that we evoked earlier, between Cairo 0 and Cairo. It's not possible to prove a failed execution in Cairo 0, and it's possible to prove a failed execution in Cairo. Now, the fact that Cairo 0 transaction, you can't prove that they failed, means that you have to resort to the design I've explained above. You have to resort to the sequencer saying, well, I can't execute it, but I can't prove that I can't execute it, so I'm the sequencer, you'll just have to trust me. The issue with that is that it's a huge censorship vector for the sequencer. It's also a way for the sequencer to just, execute validates and then not do anything and run with the money, which is obviously not ideal. And the issue with not being able to prove this is that if your transaction failed, you still want to charge the person, but how much do you charge them? You want to be able to prove that you charge them the correct amount. But it's not a non-trivial issue because from a verifier standpoint, there's no way to distinguish between crappy transactions and censorship. There's no way to distinguish between transactions that legitimately fail and a sequencer that decides, no, I'm not going to execute that transaction. So what we have in the pipeline for this specifically is twofold. The first one is Cairo zero code is going to be deprecated on Starknet eventually. You're not going to be able to execute Cairo code, and so whatever code you execute on Starknet will have to be Cairo 1. And so this means that everything you do will be provable. This is the end of a process that is called regenesis, which I think you talked about in earlier sessions. Now, it may not be included immediately, but eventually in future versions of Starknet, failed transactions will be proven, meaning that when a transaction fails, the sequencer will have to prove it failed, and however much the sequencer charges for a failed transaction, it will have to prove that this is the correct amount. That's a non-trivial piece of the StarknetOS to write. It's currently not at the top of the list, but it's something we have identified, and we know we're going to get to work sometime in the future. I see Doug is asking, what does the sequencer send the state diffs to L1? I'll explain it in a sec, but he sends the state diff before validating the proof. I'll explain it in a while, okay? Actually, ManMeet front ran me and again answered fast. Good. All right. So
there are 2 questions in the Q&A section, so I think we should get to them now.
Oh, wait. Let me just finish this slide and we're on it. Okay, so that's just a sum up of all the status of all the transaction, which we just talked about. Okay, let's get to the Q&A. How do we do that?
I can read them out for you. Franklin Omondi asks, what do we mean when we say we are building on top of a protocol? Does it mean to copy the whole code base and add your own, or is there a simple plugin?
I'm not sure what the question is, to be honest.
Franklin, if you'd like to clarify, feel free to unmute yourself. Also, just to be, as I understand this question, if you want to build on top of, say, for instance, Uniswap, you don't necessarily need to fork all of Uniswap. You can simply make calls to the Uniswap contracts, build code which is interoperable.
You're right. Okay, I think I understand the question. I can read it, and now it makes a bit more sense. So, does it mean to copy the whole code and add your own, or is it a simple plugin? Building on top of another protocol is essentially saying this protocol is deployed here on chain. I'm going to build another protocol that interacts with that one. So it's not about copying the code. It's about calling another protocol's APIs on chain. And what I mean by APIs is external functions. So yeah, it's like building on APIs, but in the blockchain. When you think about it, I mean, blockchain systems are basically open API. Any public function, anyone can use it and call it from another contract. And that's what building on another protocol means. So I see Falilat asking, what are the variables that determine the address in which an account is deployed to? Like in the case of a deploying account to Vinity address on Starknet. That is a great question. I didn't pull the documentation for my slides, but I think Pierre posted something in the chat that will give you a link to how addresses are calculated. So I'll refer you to the doc to take a look at it. In the section about account contracts, they will specify how it is created. Long story short, you can have vanity addresses because there's a salt parameter that lets you, well, you can churn through this in order to find the address you want. All right. Should I move on? Any other question? Looking good so far. Nice. All right. Now let's talk a little bit about proving how it works and what this means. So first, do we do a break? I know sometimes we do breaks in those sessions.
Yes, I was just going to say, let's do section 3 after a 5-minute break.
All right. So we meet again at 08. Make sense?
Yep.
All right. Thank you. So I'm looking at my slides. I'm wondering if I have too many of those. I'll see. There's 3 main parts remaining. One about proving, one about L1 to L2 messages, and one about data availability, and another one about next steps for you all. So we'll see. About midway, I might rush some topics a little bit, but we'll see. Should we go? Yes, Henri, go ahead. We're listening. All right. Yeah, Daniel is asking which steps should we follow for each state of the transaction. When you send a transaction, automatically you will see those states. I just want you to understand what each of those mean. So let's talk about proving. So one important thing to note is when we talk about proving, and if you have some experience doing proofs on Ethereum, you may think, oh, okay, so wait, if I write a Cairo program, do I generate a verifier? Do I generate a prover? Do I need a specific setup? Do I generate a circuit? And the one thing I want to underline here, I want to explain a little bit of context about this, but when you're writing a Cairo program, you don't generate a program. You don't generate a circuit for your program. You don't generate a verifier, and you don't need a verifier contract, and you don't need to send the proof. What is happening under the hood, and I think you've talked about this already, is that the entire validity proof aspect of it is abstracted away from you. You don't generate a new circuit. You're using one that is a CPU that allows you to do any generic computation. Cairo is an abstraction of the validity proof part of things. It pushes complexity one level above so that you don't have to care about it. So, yeah, that's basically what I just explained. And this, I'm not sure if you had a session on it already, but Cairo is a weird term because it designates so much different things, but initially, Cairo is CPU air. It is a circuit that is provable that represents a CPU that allows you to generate computation and then prove them efficiently. The prover there's an open source prover, and the verifier there is an verifier in I think there's a verifier that is not on Ethereum, but there's also a verifier on Ethereum that has been deployed and audited. Here, the big advantage is that you don't have to redeploy everything. You don't have to re-audit everything. The circuit part of it is already taken care of. Cairo, the language, is compiled to a set of instructions that get executed over this CPU. And that's the main thing. Okay, so Arsh is saying CPU air. Yeah, Cairo is so an air is the acronym of algebraic intermediate representation, which is essentially a way to represent a mathematical problem in the form of a polynomial. And an air, in our case, is let's say a circuit that represents a mathematical problem in the form of a polynomial and lets you prove the correct execution of that program, of that mathematical, of that computing problem. And the one we design is a CPU, meaning that CPUs are informatic component that lets you execute anything, any set of instructions, any program can be expressed on top of that CPU. Maybe you've seen those things where people designed a CPU in Minecraft, right, with blocks, or some people designed CPUs with wooden parts, right? Well, it's just a state machine that allows you to express any kind of computation on top of it. Well, in that case, it's computation over polynomials that you can then get to prove. One circuit to rule them all. I kind of like that line. All right, so how does it work? How do you prove Starks on Ethereum? So on Starknet, you're running Cairo program But Starknet itself, the StarknetOS, is a Cairo program, meaning that when you're moving from one block to the other, the logic to aggregate transaction and bundle them into a block and then move on to the next block is written in Cairo and is provable. And that logic executes subroutines, which are your smart contract, which are also written in Cairo. So your smart contract is written in Cairo, Starknet is written in Cairo, and Sharp is the proving backend used by Starknet that aggregates proofs and processes them. So Juan is asking, how does this compare to other ZK lengths like Noir? Is it correct to say that Noir is lower level? I don't know. I don't know enough about Noir to make an educated answer. I apologize. But I can say how it compares, for example, to CIRCOM. CIRCOM is lower level in the sense that it lets you define specific problem and specific circuit. Like think about the analogy between between CPU and ASICs. CIRCOM is a language for you to design your own ASICs and deploy them. Cairo is a CPU. So instead of defining your program and then implementing it as an ASIC, you define your program as a set of code on top of Cairo. So every time your program changes in CIRCOM, you have to redeploy your verifier. You have to redo your ASIC. Whereas every time your program changes on Starknet or on Cairo, you don't have to do anything because the circuit already exists. Okay, so when you're proving transactions, one of the big advantages of Starks is that the cost of verifying the cost of verifying grows with the workload you're trying to execute, but it grows logarithmically, meaning the bigger the program you're trying to prove, the lower the cost per unit of compute it is to verify. So instead of having your proofs be verified individually, it makes sense to bundle them into a system like Sharp that is part of a bigger proof so that you have lower cost for your individual program. So what is Sharp? Sharp is the acronym of Shared Provers, and its job is basically to aggregate what we call Cairo jobs and then bundle them into a single proof to diminish the marginal cost of verification. And such jobs may include Starknet blocks, right? So any Starknet block is a job. It's a Cairo program that moves from block 1 to block 2. But Cairo programs can also can also be used to do other things. So for example, StarkX is written in Cairo and can be used in Sharp. And arbitrary Cairo programs can also be used in Sharp. The latest example we have, for example, is a company called Herodotus, which is doing storage proofs. And recently, they started using Sharp to prove state. Sorry, they started using proofs to. I'm sorry. They started using Sharp to prove state transitions on Ethereum and to prove historical hashes of Ethereum block. So they wrote a Cairo code that proves that a specific block hash was part of Ethereum history, and that code is written in Cairo and verified on Ethereum. And which is really fun way, because when you think about it, any Ethereum block it can't access state, and it can't even access the hash of blocks that are further than 250 blocks in the past. With this kind of stuff, they've basically given access to any Ethereum contract to past state at any point in the history. So not full state yet. They're working on it, but block hashes is the first step in that direction. So that's for Sharp. So Sharp is in charge of aggregating Cairo jobs which get proven. Another important component is the Stone prover, which I think Pierre shared a bit earlier. So the Stone prover was open source actually very recently in August. It allows you to prove Cairo 0 program. So if you have any kind of Cairo 0 program, and you could execute Starknet, for example, you can generate a proof that that program ran correctly. That proof can be used either on L1 on Ethereum, or there is also with it a verifier. So you can build your own application where you get to have the two sides, right? You can generate the proof and verify it on the other end. And this is also used, for example, by companies who are doing ZK-ML, ZK machine learning, because they're able to execute machine learning jobs and then prove them, prove that they executed them correctly, and have a third party verify that they did. Okay, so we have Cairo jobs, we have a prover, and we have a verifier on Ethereum. How does the verification process works on Ethereum? So the fact registry is the first stop. So when Sharp executes a Cairo program, what it does really is that it proves that a tuple is valid, and that tuple is composed of the program hash, right? So the identity of the program being proven, the input hash, and the output hash. So in the case of Starknet, for example, the proof is the state of the previous block. The output is the state after aggregating the block, and the Cairo program hash is the StarknetOS, right? So the verifier on Ethereum, and you can see it on Etherscan, you will receive those tuples and it will verify the associated proofs. If the proofs are valid, then the tuples are saved in a fact registry, and now Ethereum knows that something was executed. It doesn't know what it is, but it can attest that that particular program was ran correctly with that input and it led to that output. So this is the very first step, right? This is the tight link where Ethereum knows something. Now, how do you build the state of Starknet on top of it? So the StarknetOS smart contracts, or the Starknet core smart contract, queries facts from the facts registry, and it will verify that the proof was validated. So it will basically be able to say, yes, there was a state transition. Now, one of the things, and before saying there was a state transition and it was valid, it will verify a bunch of other stuff. Notably, it will check that state diffs were published and that messages that were sent were published also. And it will just check, yeah. Bottom line is this. I'm going to get back into this later on. Feel free to write question. I'm going to take a look in the Q&A section. No more question. So I'm guessing that's good. All right. So at this point, we have proven the state transition, and the StarknetOS is aware that we move from one state to the other, right? So let's sum up what we talked about in terms of proving. Smart contract execution is part of a Starknet block. A Starknet block is a Starknet job. A Starknet job is part of a Sharp job. Sharp jobs are proven off-chain and then verified on-chain. Verifying generates facts, and then the logic to maintain the state of Starknet is managed by a smart contract on top of that logic. You can see the different layers of verification and proving here. I'm hoping that makes sense. I'm going to talk a little bit about data availability. Now, first, let's talk about what the problem is. If we take back what we discussed just earlier, so the StarknetOS takes a tuple, input, the hash, the output. Now, in the case of Starknet, I mentioned it, input is the state at block n, output is the state at block n+1. But if you use the full state of Starknet may be in gigabytes. You know, the state of Ethereum is very big. There's no reason why the state of Starknet wouldn't be big also. So if you do this, you're going to store at every query, at every fact, you're going to store the full state, and that's very inefficient. So instead of using the state, we can say, for example, we can just state the we can just store the state root. Now, that's kind of risky because now your inputs are the state root, but what happens if that state root disappears? What happens if the state disappears? Imagine that, boom, you lost it. Your computer crashed or the sequencer's computer crashed and you lost the state. What happens? Well, in that case, nobody can move Starknet anymore because the system has moved from block n to n+1 to a new state, but that state is lost and there's no way to reconstruct it. So the system will be forever lost, forever stuck at block n+1. And that's an issue. So what Starknet does, and here there's a big difference between what validity rollups are and Validiums are. So what validity rollups do is they say, okay, we can't afford to lose the state. We need people to be able to reconstruct the state. So what we do is we publish the state on Ethereum. We don't need to store it. We don't need to make it a smart contract variable, but we need to publish it. It needs to be accessible. So you put it in an event. It's not part of the smart contract state, but it is part of the blockchain. So it's there. You can reuse it. The other thing we can do to save space here is instead of publishing the whole state each time, we publish state diffs, meaning we just push what is the difference between one state and the other. Then the Starknet core contract verifies before it moves from block n to n+1, it will verify that the proper state diffs were published and emitted as events. And if they were, it will say, okay, I can move from block n to n+1. That works. That's very safe, but it's very expensive. Right now, I think it's 98% of the transaction cost, which is kind of crazy when you think about it, because if you divide the price of storage on Ethereum by 10, it means that the cost of data is still close to 90% of your transactions, which is mind-blowing, right? I mean, you could divide it by 10 and it will still be 90% of your cost. Because then you have 9.8 plus 2, and 9.8 plus 2 is close to 90%. I mean, 9.8 is close to 90% of 12, right? So currently, data availability costs are the main cost for validity rollups like Starknet. The other option is what is called Validium. Instead of publishing data on chain, I mean, why do we need to be paranoid about it? Maybe instead of having just one sequencer, like the risk is what? If we lose the data, if the sequencer loses the data, then everything is lost. It's not like storing data is that difficult of a deal, right? I mean, a lot of companies are doing this. Google does it. They have redundancy. They have a lot of, data safety mechanism. So why not? Well, I mean, technically, this can work. There is a trade-off, though, because if a person storing the state decides to just not share it, that's an issue. So one thing Validiums are doing is they're working. I mean, the whole data availability space is really interesting because when you think about data availability, most people think data storage, but in reality, what data availability is about is data publication. It's not about who holds the state at any given point in time. It's about proving that the state was available at some point for somebody to download. And that's what stuff like Celestia are about. And when you think about it, that's what we're doing with ZK rollup is about too, right? With the validity rollups, we make sure that the data is part of the history so that it was published sometimes, but if and when Ethereum nodes start dropping all part of the state or the history of the chain, this will be lost. So in general, you have those two constructions. Validity rollup, where state publication is verified on-chain, and Validiums, where state publication is not verified on-chain, but taken care of off-chain. It's usually much cheaper, but less safe. Now, something in the middle is Volition. ¿Por qué no los dos? Why couldn't we have the best of both worlds, right? Maybe we could have instead of having one state, we could have two states. One state where things need to be pushed to L1 and one where things don't need to be pushed to L1. That way we can accommodate both people. The people who want to have data on-chain and the people who don't want to have data on-chain. This essentially leaves this decision, instead of saying, oh, there's two different networks, it leaves this decision to the individual devs. That particular data, is it worth going on-chain? Is it not? I mean, if it's your balance for ETH, yeah, maybe you want it on Ethereum. If it's the metadata for that sick penguin NFT you have, and it's the color of its hat when it's winter, maybe not worth putting on Ethereum. I don't know. But then at that point, you let dev decide what works for them and for their users. And that kind of construction is called Volition. It's something we're working on. We initially thought Volition would be live by the end of this year. It turns out to be a bit different than what we expected. But we'll get to it later on. But in the meanwhile, what was further in the future and seems to be closer is the implementation of EIP-4844. So the data availability problem I just explained is not something that is unique to Starknet. It's something that affects optimistic rollups and ZK rollups in general. So Ethereum is in the process of adding a feature through EIP-4844, which makes it possible for anyone to publish data on Ethereum that is provably kept by nodes for a week and provably accessible by any member of the network for a week, and then deleted, or then is not mandatory to keep for all nodes. Some nodes will keep them, some nodes won't, but it's basically a way to ensure data publication, which is what I discussed before. It's not about storing data, it's about making sure it was published at some point. EIP-4844 is a really interesting construction, and it's also a great avenue for Starknet to reduce its cost. So instead of publishing data as part of events, which is expensive, Starknet will publish its state diffs through EIP-4844. And if you're wondering, is it still safe? Well, that's a good question. From most people we talk about this with, they consider it as safe as the alternative. So there was a question. Manmit is saying penguin NFTs are very valuable. I know, that's why I took this example. It's not easy to choose. And yes, Daniel is saying dank sharding. Yes, exactly. 4844 is dank sharding. It's dank sharding. All right. So summing up on the data availability part. So data availability is a tough nut to crack. It's something that is very specific to ZK rollups and to Ethereum. I mean, it's very specific to blockchain networks. And I'm not sure anyone has found a silver bullet there yet. 4844 will surely be an interesting add-on to Ethereum, and we'll see what effect it has. Validity rollups use L1 for data publication. Validiums use something cheaper off-chain. Volition is a construction that combines both. That's the main outcome I wanted you to remember here. And I hope, can I get a quick show of like, if you are learning something in that session, can you give a thumbs up? If it's something that is meh, can you put another emoji so that I know that I need to do something differently? Okay, and Evans is saying archive nodes will decide whether to store all data or not. Is it only applicable to full nodes? So archive node are a different creature. On Ethereum, archive node, they don't just store the history of the chain, they also So there are two kinds of history of the chain on Ethereum. There's individual transactions, and when you replay transaction, you have the state of Ethereum at each block. So you have the state at block 100, you play transaction, you have the state at block 101, and so your state moves on, right? Archival node are nodes that for each block will store a copy of the state. Meaning instead of taking the state at block 100 and applying stuff on top of it, and then having state at block 101, they will make a copy of the state at each step. This is extremely heavy on your, this is very, how do you say that? Is very heavy on the memory of your machine. That's why archival nodes are very expensive to run and hard to run. As far as 4844 is concerned, I'm not entirely sure. I'm pretty sure I would be surprised if node operators don't give you the opportunity to keep everything that was published. So I'm pretty sure some nodes will decide to keep the data and some others won't. But being a full node won't require for you to keep all the data that was published in blobs. Blobs being the structure of data that is used in 4844 to do stuff. Yeah, so that's this. Now, what it means to be a full node, I think eventually also on Ethereum, at some point, full nodes will be expected. It will be okay for full nodes to drop part of the state or drop part of the history. But that's another story, so we'll see. Okay, now let's talk a little bit about L1 and L2 messages. I'm going to go quick on that part because I think you already discussed about it. So I'm going to go pretty quick. So when you think about bridging and L1 to L2 communication, people think about bridging tokens, right? So you think about bridging ERC20s, you think about bridging NFTs, but in reality, blockchains are used for way more things than just tokens. They can be used for computation, permissions, instructions. So what if you could do the same with your bridge? What if instead of building a token bridge, you could pass data? If you can pass data, then you get to design your own protocol on top of L1, L2 communication instead of just having a token bridge. So let's see how this works in practice. How do you talk to Ethereum from a Starknet contract? Well, it's actually really simple. There is a syscall in your smart contracts. I don't know if you looked at it, but that basically tells in which you can basically say, okay, I want to send a message to that smart contract, and here's the payload. So you basically say, hey, here's a bunch of data, do something with it. Then that message is registered by Starknet. It is indexed, and for a while, it is pending, meaning that it is waiting for the next proof to go to Ethereum. Now, once a proof is generated with the block your message is in, that proof in its state diffs will include the message that you sent. And that message will be logged as an event on Ethereum, as you can see, right? So it specifies who is sending it from L2, to whom it is sent, and what is the payload. Now, a message is identified by its hash. It has a counter. So when you send a message to Ethereum, the content of the message is not stored. Its hash is, and an associated counter is. And then it's kind of like the post office. When your message reaches Ethereum, it doesn't trigger an action. It sits there in a smart contract and in the Starknet core smart contract. And if the recipient on L1 needs to do something, it needs to go and pick it up, like a parcel at the post office. You show up and say, "Hey, I received the parcel. Can I do something with it?" And so the smart contract will say, "Hey, do you have something for me?" If Starknet Core has something, it will say, "Yes, I have something for you." And then your smart contract can act upon it. That's the hook you need to execute something and to be sure that something came from L2. This smart contract can only be activated if something came from L2 and was proven. Now, those messages are transmitted with proof, and currently proofs are sent every few hours, so this takes a bit of time. It's hard to debug and it's pretty painful. Luckily, there's a bunch of tools for you to do this more efficiently. I see Ivan. I mean, I know Ivan was here at the beginning. I saw him say hi with the emojis, and he has Shard Labs is developing a set of tools to allow you to emulate this kind of stuff and work locally with these kind of things and debug your protocol. So if you want to build on this, make sure to ask Ivan. So BB is asking, is it possible to automatically consume the message on L2 and trigger another operational function? So the message is consumed on L1. Is it possible to automatically consume it? Yes, you can have keeper networks like Gelato, for example, that will make sure your message is consumed. You can build the required network of people that will trigger this thing on L1. It doesn't need to be permissioned. So in order to claim the parcel, it needs to be executed from the Ethereum side. Yes, a transaction needs to be sent. Like the L1 recipient needs to be triggered so that it goes pick up the parcel. It goes verify that something happened. Kind of like when a DeFi application you want to deposit USDC in a DeFi application, you will first authorize the contract on the USDC contract. And when you're trying to deposit, what the contract does is it goes to USDC and say, hey, am I allowed to do this? Yes. And then it does something. Here it's the same. When you want to trigger it, it will say, hey, did I receive a message from L2? Yes. Then I do my thing. Okay. Now let's see the opposite route. How do you talk to Starknet? How do you write an application on Ethereum that talks to Starknet? Here, actually, well, there is an API on the Starknet core contract that allows you to send a message to L2. It's basically an external function on a smart contract where you have sort of the same parameters: the to address, the selector, and the call data. What is that parameter, selector? Well, selector is something we made to make your life easier. The other way around, so when you send a message from Starknet to Ethereum, the message stays at the post office until the smart contract comes and pick it up. When you send a message from Ethereum to Starknet, the message gets delivered exactly at the recipient. So it gets delivered at a specific mailbox, which is a specific function that is programmed to be executed when there is a message. And that function is called the L1 handler. And you need to specify its selector so that when it is executed on L2, the message knows which function to trigger. So you specify which contract you want to call, which function you want to call on that contract, and what the payload should be. All right. So what does a L1 handler look like? It's basically a function, but it has a special decorator here saying L1 handler, and it has to have a few specific contract parameters. For example, I think the first parameter needs to be from address. So you need to tell who is sending that message, and then you can add whatever you like. That's just an example here. So here, for example, my function just verifies that that from address is a specific address, but you can receive messages from anyone you like. Now, the big difference here is that when you go from Starknet to Ethereum, we wait for a proof to be passed. When you go from Ethereum to Starknet, actually, we just wait for the transaction that sends the message to be, how do you say it? It's not validated. It's not solidified. It is, help me here, finalized.
What?
There you go. So it waits for the transaction to be finalized. It waits for 10 block confirmation, and then it is executed on Starknet. So they're consuming immediately. They're a bit of a pain in the ass to debug. StarkScan has really cool features there that help you see when your message was sent to Starknet and what transaction it led to be. So the transaction that will execute your L1 handler is executed directly by the sequencer. So the sequencer is able to call your L1 handlers and execute them. Now, how is this safe? Because we said when you send a message from Starknet to Ethereum, it waits for the proof. there's no proof from Ethereum to Starknet. So how does it work? When a message from Ethereum is executed on L2 on Starknet, it activates a specific flag that will be part of the state diff in the next iteration, in the next proof, when the next proof is sent to Ethereum. So when the next proof is sent to Ethereum, the Starknet core smart contract will do what we discussed so far. It will verify the proof. It will verify that the data was published. It will verify that the messages to L1 are present. It will also verify that all the messages that were executed on Starknet indeed are part of, were sent on L1. So meaning you can't execute an L2 message if it wasn't called, otherwise the next proof is not going to be valid. Okay. James Autopilot, feel free to leave. We don't need you anymore. All right. I see I see some questions. I'm assuming that they were answered by Pierre. So Juan is asking, in other words, you must prove you're the legitimate recipient of this parcel by showing your secret tracking number. Not really. On Ethereum, you're supposed to prove you're the recipient of that message by showing your ID, meaning that if you're the recipient, you're a smart contract. You have a specific address, and only the account with that specific address can pick the parcel up. So it's not a secret message. It's just like you're that contract or you're not. I hope that makes sense. All right. I've rushed this part a little bit, but I think we're there. I think this was all the technical content I had for today. So if there are no more questions, and feel free to ask more questions here before I go to the next part. So BB is saying, I made a mistake. I meant to say from L2 to L1. So when the message from L2 gets consumed in L1. Okay, I'm not sure I have the full context there. Feel free to... okay, so indeed, BB was asking, how do you auto-consume messages on L1? Well, you can build your application around that. You can use an automation tool like Gelato, or you can just integrate with any keeper network. And with this, I'm done for today's presentation technical side of things. I want to give you a big round of applause first. Congratulations, you made it. This was a yeah, exactly, party time. Emojis. This was a long time, and I think it is by far the most successful Basecamp cohort we've had so far. A lot of people registered and a lot of people showed up. You're 50 on the last session, and this is a huge achievement. It is a huge achievement for all of you. First of all, because I'm just gonna, sorry, I just need a second. All right, yeah, I apologize. Yeah. Anyway, so I was saying this is great. This is a huge thing for all of you first, because following a class for 6 weeks, 2 hours a week is non-trivial. It takes a lot of time and dedication, and we're very grateful for that. We're very, very grateful for the time you spent learning about what we're building at Starknet and see how you can do stuff, because time is the most scarce resource, and brain time from talented developers like you all is even scarcer. So thank you for that. I also want to extend a huge thanks for all the tutors we had for this cohort. I'm thinking about Darlington, Pierre, Robert, all the people, and David obviously, and Manmeet who helped with all this. Like, I think we can indeed give them a huge round of applause, because they were very dedicated. They're dedicated community member, and it's great to have them on this journey. Now, let's talk a little bit about what's next for you attendees. You made it through Basecamp. Now what? Where do we go from there? And what's next for you. So here are a bunch of slides giving you a few leads as to what you can do or where you can go. The first thing you can do is start a community. At the end of the day, I like to say that blockchain networks are really cool. They're really interesting to look at, but they're nice technical creatures. They're nice technical constructions, but at the end of the day, they're about people. They're only as powerful as people using them. And if you want people using them, you need to tell people about it. And also, if you like talking about Starknet, then it's pretty cool to have people around you to do that. So Starkware, has a program to help people organize meetups close to where they live. It's all the details are in the document of which I shared the link here. Basically, give you a grant of $1,000 to organize a meetup. If you want to organize one a month, you'll get $1,000 a month to organize those meetups. And we'll be happy to support you, grow the community around you. We'll help you find speakers. We'll help you find sponsors. We'll help you find ways to make this happen in the best way possible. And a really easy way to get people is to basically, you follow Basecamp, teach Basecamp to other people, like study, get all the materials we have, they're open source, and talk about this with friends and do it with other people. The other thing I want to invite you to is the ecosystem orientation call. So this is a link to a Calendly where you'll get on a call with me. I'll repeat most of what I'm saying right now, so you may learn a few things, but not a lot. The idea with this call is if you have an idea for a project you'd like to experiment with, let's say you think, oh, I'd like to build this kind of library in Cairo, or oh, I'd like to build this tooling for the infrastructure of Starknet. We give builder grant to interested and talented people, provided they've done some work. You followed Basecamp, so you probably fit that criteria. The grants are not super big. They're 2.5K USD each. But I'll be happy to extend them to you if you want to keep exploring your Starknet journey. It's also a great way to, like if you're a freelancer, for example, to have peace of mind to spend some time there without worrying about rent. Another thing I want to mention, and that's something that is also a prerequisite to get the Builders Grant I just mentioned, is the mentoring program. So maybe you're interested in building more stuff on Starknet, and you want to, but you don't want to go alone, and you have some questions. And sometimes asking questions on Discord or on Telegram can be a bit daunting. The mentoring program is really about connecting you to experienced builders so that they can answer your question, and you get to have somebody with you along the way. Yeah, I'll send the links for the previous slide. I shared the link for the slides earlier, so you can click there. Like all those links are clickable. Let me share it again. Oop. All right. So getting paired with a mentor is the best way for you to make sure that you'll. It's the best way for you to be able to ask questions, make friends, and stick around in the ecosystem. And we'll be happy to connect you with somebody who is either, who has similar interest to you or is in the same region as you. It's still experimental, meaning that it's not something we've done for a very long time so far. We're still perfecting it, but, come be our guinea pig. I promise it's going to be fun. The first thing you can do is contribute to open source project. I'm pretty sure that by now, a bunch of you are already registered on OnlyDust. Those who are not, I highly encourage you to do so. OnlyDust is a platform that connects open source projects. A lot of them are in the Starknet ecosystem. They connect open source projects with contributors who want to contribute on an open source project. And it is a really good way for you, especially if you don't have a specific idea, it's a really good way for you to actually start toying with the technology, start writing Cairo contracts, start to write code for infrastructure of Starknet, and actually get paid for it. Those contributions are not free, so when you contribute, you get rewarded for your contribution. You get paid. And so it's something that's really useful. For example, if you're a freelancer, it's a great way for you to actually diversify a little bit your activity, figure out if you can, if there are interesting stuff to do there. I also mentioned that it is an amazing opportunity and it's an amazing way to build your portfolio. If you're looking for a job at some point, if you're looking for freelancing opportunities, having a portfolio where you can show if you can show code that you did and projects you contributed to, that goes much longer than any CV or any call. So it's a great way for you to show that, yes, you know what you're talking about, that you've used those projects in the past. It's also a great way to meet other people, instead of doing something alone or you work with other people. It's a great way to, see people you like and also see people you don't like. Open source projects are really good because you can go in and out whenever you want. So it's low commitment. It's not like a company where you join and you have to stay. You can work a little bit. If you like it, you stay. If you don't, you move to another project. So it's a really good way of seeing how you like to work and who you like to work with. And also mention that it's a great way for you to develop and use cutting edge tools. The things that are being developed there are definitely cutting edge, and knowing how to use them is a great way for you to build your skill set and to be a step ahead of the game, basically, right? So I strongly suggest you go there. I was talking with Abdel earlier, asking him, hey, where should people contribute? There are 2 projects on OnlyDust that can benefit a lot from contribution. If you're looking to write Cairo code, you should take a look at a project called Satoru, Satoru. If you're looking to write infrastructure code and specifically Rust code, you should take a look at, I forgot, let me check. Yeah, of course, Madara, the L3 stack we were mentioning earlier, they're looking for Rust developers. So if you know how to do Rust, or if you want to learn how to do Rust, you should take a look at Madara. I'll also add that the community is really friendly. They will help you out. They will help you respond your first PR. There's different levels. So they're a really great way of onboarding the ecosystem. Now, the final thing I want to mention is, maybe you're interested in something else. Maybe you're interested in not starting a project. You don't want to try something for fun. You actually want something more. You want to build a company. You want to be something big. You want to be something meaningful. In that case, we're also super interested in talking with you, and there's plenty of stuff we can do to help you. We don't have a systematized ways of addressing people who want to build company, but we want to find one. So we want to talk with you. The link here is for my email. It's Henri, Henri, @starknet.org. Feel free to use it for other purposes, but feel free to use it particularly if what you're looking for is building a company. We'll be happy to discuss what we can do to help you. We'll be happy to connect you with incubators. We'll connect you with fellow entrepreneurs in the ecosystem so that you can exchange with them. And if you're looking to raise funds, we'll be happy to connect you with people who can, with basically what we can do to companies is help them refine their pitch, their value proposition, so that they're more pertinent when they talk to VCs, and then introduce them to VCs who are top tier to make sure that they can make the most of their raise. So we'll be happy to help you with that also. And that's what I wanted to mention to end Basecamp, right? So if you want to do more, just I detail what all the things you can do. I'll conclude by saying this: you're at the right place at the right time. There is a lot of things to build. I think when you see where Starknet was a year ago and you start thinking where Starknet will be in a year, it's pretty mind-numbing. And it's crazy the amount of stuff that needs to be done, both on the infrastructure side, both on the app side. It's going to be crazy. It's going to be super fun and super interesting. And we're super happy to have all of you along the way. We'll be super happy to discuss, to see whatever we can do on your Starknet journey. We're really happy to have had you all in Basecamp for that particular cohort. I also want to say that if you stick around, this is great, and we'll be happy to talk with you. If at some point this is not what you need anymore and you want to drop out and you want to go out of the community, this is perfectly fine. We understand that not everyone is committed all the time, but we'll be super grateful to understand why. We won't try to convince you to come back, but if you can tell us where we can get better, tell us what we can do to make the ecosystem better, more welcoming to newcomer, and basically anything you can tell us to make the network better, we're always listening, and we're always willing to do better. And it's the same for people who stay, by the way. Any critics, anything you feel like, hey, this needs to be made different. If you can't fix it yourself, then tell us and we'll do our best to fix it. And that's it for my presentation today. Thank you. And I'm looking forward to what's next for all of you. I'm happy we have 2 more questions. Oh, nice. If there are more questions, feel free to ask them. I'll be here for a few more minutes. And yeah, feel free to ask your question in the chat or open your mic. Yeah, or actually, let's wrap it up. Thanks, everyone. I'm looking forward to seeing you soon. I shared my presentation with you in the chat, so feel free to follow the links and hit me up there.
Thank you, guys. See you.
Cheers.
Meet Robert. See you guys.
Bye-bye. Thank you.